In this video, we're going to do a little bit more on working with divergence in curl. There are some key properties for divergence in curl that we have to keep in mind. If I'm given a real number constant C and the vector fields F and G, the following properties will apply. My divergence properties are that del dotted with the sum of F and G is equal to del dotted with F plus del dotted with G. Del dotted with a constant times a vector field F is equal to the constant times del dotted with F. For my curl properties, del crossed with the sum of F plus G is equal to del cross F plus del cross G. And del crossed with a constant times the vector field F is equal to the constant times del cross F. Now, suppose that F is a conservative vector field on an open region D of R3 space. I know that F is equal to del phi, where phi is a potential function with continuous second partial derivatives on D. Then del cross F is equal to del cross del phi, which is equal to 0. This just tells me that the curl of the gradient is the 0 vector and F is irrotational when I have a conservative vector field. Del cross del phi is the determinant of a 3x3 matrix with the first row populated by I hat, j hat, k hat, the second row populated by the del operators, the partial with respect to x, the partial with respect to y, and the partial with respect to z, and the third row is populated by phi sub x, phi sub y, phi sub z. This gives me phi sub zy minus phi sub yz in the I hat direction, plus phi sub xz minus phi sub zx in the j hat direction, plus phi sub yx minus phi sub xy in the k hat direction. But remember Clairaut's theorem that said that the order of integration when I'm taking a second partial derivative doesn't matter, so that phi sub zy is equal to phi sub yz, and so on. So that this tells me that del crossed with del phi is going to equal 0. Now suppose I have a vector field with vector components fgh, where fg and h have continuous second partial derivatives. Then del dotted with del cross f is equal to 0 as well. This just tells me that my divergence of the curl is 0. If I want to compute the divergence of the curl, I take del dotted with del cross f. This is equal to the partial with respect to x of the quantity the partial of h with respect to y minus the partial of g with respect to z, plus the partial with respect to y of the quantity the partial of f with respect to z minus the partial of h with respect to x, plus the partial with respect to z of the quantity the partial of g with respect to x minus the partial of f with respect to y. This becomes the quantity h sub yx minus h sub xy plus the quantity g sub xz minus g sub zx plus the quantity f sub zy minus f sub yz. But again, Clairaut's theorem tells us that the order of partial differentiation does not matter, so that the divergence of my curl is in fact 0. We've seen that we can combine the gradient and the divergence in curl in various ways, but there are some ways that we can't combine them, and we need to make sure that we understand what we can and cannot do. We cannot take the gradient of the curl. This means I cannot apply the del operator to del cross f. I also cannot take the curl of the divergence. This means I cannot take del and cross it with del dot f. Both of these are undefined, but there is another combination that will be extremely useful. It's called the Laplacian. I can take the divergence of the gradient of a scalar valued function u. This means I can take del dotted with del applied to u, which just gives me del squared u. This is called the Laplacian of u. Let's see what it looks like. Del dotted with del u is equal to the partial with respect to x of the partial of u with respect to x, plus the partial with respect to y of the partial of u with respect to y, plus the partial with respect to z of the partial of u with respect to z. This just becomes the second partial derivative of u with respect to x plus the second partial derivative of u with respect to y plus the second partial derivative of u with respect to z. There is also a product rule for my divergence. If u is a scalar valued function that is differentiable on a region D, and if f is a vector field that is also differentiable on D, then del dotted with del applied to u times f gives me del u dotted with f plus u times del dotted with f. This product rule is very important. It doesn't show up frequently, but you need to be sure and look for it if you need to use it. Let's work an example. I want to prove the identity that del dotted with del applied to 1 over the magnitude of r squared is equal to 2 over the magnitude of r to the fourth. First, I want to use the quotient rule. Del of 1 over the magnitude of r squared becomes del of 1 over x squared plus y squared plus z squared, which is equal to negative 2x over the quantity x squared plus y squared plus z squared squared minus 2y over the quantity x squared plus y squared plus z squared squared minus 2z over the quantity x squared plus y squared plus z squared squared. This is just equal to negative 2 times the vector r over the magnitude of r raised to the fourth power. Now I have to use the fact that del dotted with r over the magnitude of r raised to the p power is given by 3 minus p over the magnitude of r raised to the p power. Del dotted with negative 2r over the magnitude of r to the fourth is equal to negative 2 times 3 minus 4 over the magnitude of r raised to the fourth power, which is equal to 2 over r to the fourth power, QED. Now you get to try it. Pause the video and prove the given identity. When you're ready, restart the video to check your understanding. You need to prove that the gradient of 1 over the magnitude of r cubed is equal to negative 3 times the vector r over the magnitude of r raised to the fifth power. I first want to use the quotient rule again. The gradient of 1 over the magnitude of r cubed is equal to the gradient of 1 over the quantity x squared plus y squared plus z squared raised to the 3/2 power. This gives me negative 3x over the quantity x squared plus y squared plus z squared to the 5/2 power minus 3y over the quantity x squared plus y squared plus z squared to the 5/2 power minus 3z over the quantity x squared plus y squared plus z squared to the 5/2 power. This is equal to negative 3 times the vector r over the magnitude of r raised to the fifth power. And we're done. This is how I can work with divergence and curl in 3 dimensions. Be sure and let me know if you have any questions.